Alright, so in this video we are going to be concluding the topic 4 of Electrochemistry in Chemistry 0620 Cambridge IGCSE, finalizing the topics, the remaining topics, which are electroplating, rusting, metal displacement reactions, extraction of iron, and extraction of aluminum. So I'm going to try to divide this last topic or this last sheet also into two videos. The first one is basically going to cover the displacement reactions and the extraction of aluminum. The second video is going to cover, or the second part of this video is going to cover the extraction of iron, the rusting, and the electroplating sections. Okay, so let's begin. Metal displacement reaction. Metal displacement reaction is a type of redox reaction. Before we continue here, I just want to ask you, what is a redox reaction? Okay, if you got the answer correct, the answer is going to be a chemical reaction that shows both oxidation and reduction at the same time. We took this in the beginning of our videos in electrochemistry topic 4. So it's a type of redox reaction in which a more reactive metal replaces a less active one from its compound. Basically, the more active metal will replace a less active metal in the compound in the redox reaction, okay? Here are some key points to consider. The tendency of a metal to lose electrons is a measure of how reactive the metal is. Hence, a metal high up on the reactivity series loses electrons easily and is more reactive than the ones below it. Basically, the tendency or the ability for an element to lose electrons defines how active it is. So an element that is more active will lose electrons at a faster rate compared to an element that is less active, which will lose electrons at a slower rate. Alright? And we know, according to the reactivity series of metals, as you're going from down to up, reactivity is increasing. So the highest reactive metals have a higher tendency to lose electrons. Of course, any metal would replace another metal below it in the reactivity series because the metal higher is more active than the metal below it. More reactive metals are better reducing agents as they lose electrons and form ions more quickly than less reactive metals. Clearly, because more reactive metals are more faster at losing electrons, so they are better reducing agents because they become oxidized much faster. Alright? Now, what happens during a metal displacement reaction? The more active metal is oxidized because it loses electrons, okay, and it acts as a reducing agent. The less active metal, it is reduced. Why? Because it acts as an oxidizing agent. It gains electrons in the reactant side. Here's an example. So zinc plus copper sulfate gives us zinc sulfate plus copper. Zinc is more active than copper, so zinc will replace copper from its compound and it will form the new compound. When you write the new compound, be sure to use the cross-arrangement method to ensure the charges or oxidation number of the new compound that you write. Here is another example. Actually, let's go to example 3. So over here, there will be no reaction. Why? Because Ag is less active than magnesium in the magnesium nitrate compound, so it will not replace it, okay? Now, there's a note to consider here. Copper plus any of these acids, okay, like sulfuric acid, hydrochloric acid, any of these acids, copper will not react with any acid with hydrogen. Why? Because copper is less active than hydrogen. So for example, copper plus hydrochloric acid, there will be no reaction because copper is less active than hydrogen, so it will not replace it from its compound, okay? So likewise, according to the rules of the metal displacement reactions, this reactivity series of halogens follow the same rules, going from up to down in the halogen periodic table in this series, group 7, I believe so. Fluorine, chlorine, bromine, iodine. Fluorine will react the fastest, then chlorine, then bromine, then iodine will react the slowest, okay? So same thing, more active halogen will replace the less active halogen. So for example, iodine plus sodium chloride, there will be no reaction because iodine is less active than chlorine. But here there will be a reaction or the displacement because chlorine is more active than bromine, alright? So it applies the same rule. Okay. So this is just some common examples here. You can review this if you like. Alright, basically showing that which reactions will result in a displacement reaction because the metal is more active, and which reactions will not result in a displacement reaction because the metal is less active, okay? After you've reviewed this, let's have a look at how do we extract aluminum from its ore, okay? So before I jump to the extraction of aluminum from its ore, I want you to understand the key terms here, the key terms that we're using. What is an ore? An ore is a natural mineral from which a metal can be extracted from. Any natural mineral from which you can extract a metal, okay? So aluminum has its ore, and any natural mineral from which a metal can be extracted from has an ore, okay? So what is the main ore of aluminum? Of course, aluminum can be extracted from many ores because aluminum is present in many natural minerals, correct? There are so many minerals out there, and so many of these minerals contain aluminum. So there could be so many ores out there. But what is the main ore of aluminum? What do I mean by main ore? The main ore of aluminum is the ore that has the highest percentage of aluminum present inside it. This ore is bauxite. Bauxite is the main ore of aluminum that contains Al2O3, aluminum oxide. Okay? Why do we choose aluminum for extraction? Three major reasons, which they will probably ask you in the exam. It is a light metal, it conducts electricity well, and it resists chemical change, like rusting and corrosion. We will learn this by the end of the extraction of aluminum. How does that work? How do we extract aluminum? Aluminum is extracted by electrolysis. Why is this important to know? One of the reasons, yes, for general knowledge, aluminum is extracted by electrolysis. And another reason is because we will compare this to the extraction of iron, which is extraction by a blast furnace. Okay? Aluminum oxide is insoluble in water and has a very high melting point. Why does it have a very high melting point? Because the bauxite, the ore of aluminum, has a very high melting point. Alright, coming to the beautiful extraction of aluminum by electrolysis. So, this is the name of the process. It's in French, okay, and I personally hate French, so I'm not going to say the name, okay, because it's a bit hard to pronounce. And it's also not required, to be honest. I just wrote it there for fun, okay? But basically, yeah, let's begin. Step 1. So, to extract aluminum from its ore, the first step, you take the ore, which is bauxite, and you purify it. Bauxite is purified to obtain pure aluminum oxide. What we want, we need pure aluminum oxide, okay? So we take the bauxite ore, we purify it, and we obtain pure aluminum oxide. This purified aluminum oxide that we achieved, okay, it is dissolved into molten cryolite. Molten cryolite is another ore of aluminum, okay? Why do we dissolve the pure aluminum oxide obtained from bauxite into molten cryolite? We do this to reduce the melting point of bauxite because bauxite has a very high melting point, okay? Almost about 2000 degrees Celsius. Hence, it will use a lot of energy for extraction and it will be very, very expensive. So, we dissolve the purified aluminum oxide into molten cryolite to help reduce the melting point, okay? After this, the resulting mixture of aluminum oxide and cryolite is electrolyzed in an electrolytic cell made from steel and lined with graphite. This is the electrolytic cell in which electrolysis of or extraction of aluminum takes place in, okay? By the end, the process is called extraction of aluminum by electrolysis of molten bauxite. From here on, we're going back to our previous topic or previous video in electrolysis, in which we learned what is electrolysis and how can we identify electrolysis equations. So if you can tell me what is the first step, or ask yourself, what is the first step? Yes, it is writing the decomposition equation. Identify the decomposition equation of aluminum oxide. Al2O3 is decomposed into 2Al plus 3 oxygen. Okay, it must be a balanced equation. Okay, so now identify the positive cation, the negative anion. The cation is aluminum, right? So it will go to the cathode. What happens at the cathode? Reduction, gain of electrons in the reactant side. Aluminum plus 3 will gain 3 electrons in the reactant side, so molten aluminum is formed at the cathode. Oxygen is negative, it will move to the anode for oxidation and it will lose electrons in the product side. Again, oxygen is diatomic and there's 2 oxygens, so oxygen will lose 4 electrons in the product side. So oxygen gas is formed at the anode. Here's the structure of the cell, okay? So you have the electrolytic cell, electrolytic solution of aluminum oxide, and then graphite lining of the anode and graphite outside from the cathode. This is the molten bauxite, aluminum oxide, the electrolytic solution that decomposes into aluminum and oxygen. Now I just want to take a brief talking about cryolite, okay, which is the other ore we mentioned during the process of aluminum extraction. This is the ore that we use to reduce the boiling point of, melting point of aluminum, okay, in the extraction of aluminum. The cryolite exists as sodium aluminum fluoride, Na3AlF6. Na3AlF6 is decomposed into 3Na plus Al3 plus 6 fluorine minus 1 charge, where sodium is liquid, aluminum is liquid, fluorine is liquid. Okay, so some key points to consider about cryolite is cryolite isn't the main ore of aluminum. Why? Because percentage of aluminum is lower in cryolite and higher in bauxite. Amount of aluminum collected in bauxite is greater than cryolite. Cryolite melts at this much degrees Celsius. After melting, it works to dissolve bauxite. When cryolite melts, it gives a large amount of free ions to increase the cell conductivity. So another one of the reasons why we use cryolite, other than reducing the melting point, is to increase the conductivity of the cell by releasing free ions after the melting of cryolite. Cryolite also reduces air pollution as less fuel is used due to less amount of carbon dioxide emission. Alright, so now I want to review the gases that are formed at the anode during aluminum extraction. In the extraction equations that we had a look at in the previous page, we saw that oxygen was formed at the anode, correct? But there are other gases. Of course, oxygen is formed at the anode by oxidation, like we studied. Another gas is fluorine. Where does fluorine come from? From the cryolite. Cryolite, when you decompose it, you have fluorine, okay? Fluorine is formed at the anode by oxidation as well, okay? So the oxidation loss of electrons, so fluorine will lose 2 electrons. As it is only diatomic, fluorine moves from the cryolite to the anode. The last gas that is formed in the anode during aluminum extraction is carbon dioxide. Carbon dioxide, CO2, is formed due to burning of anode bars. Burning of anode bars? The anode bars burn away? Yes, they do. The anode bars burn due to 2 reasons. High temperature in the cell and a high concentration of oxygen at the anode, because the carbon reacts with the oxygen at the anode and it begins to burn away the anode bars. This is why the anode bars need to be replaced from time to time. Alright? Now I'm gonna go through some practice questions. Name another metal that could be formed at the cathode. It is sodium. But why does sodium not form? And why does aluminum form? Like we said, the less active metal reacts, aluminum is less active, so it will react first at the cathode. Last question, very important, not only for your exam, but also for general knowledge. Why does aluminum not rust like iron? Have you ever wondered that? Well, look, when iron reacts with oxygen, it forms a weak layer of iron oxide, Fe2O3. It's so weak that's easily removed and another layer is formed. So iron reacts with oxygen, it forms Fe2O3. It's a weak layer, so it's removed, another layer is formed. Then it's removed, another layer is formed. So layers keep on forming, resulting in rust, okay? Aluminum, on the other hand, will react with oxygen and it will form a strong, non-reactive layer of aluminum oxide. This is so strong and it will prevent any further reaction from aluminum, resulting in corrosion or rusting. So iron will form a weak layer that will keep resulting in more and more reactions, forming many layers. Aluminum will form a strong non-reactive layer that will stop at once and not result in more layers forming, and there will be no rust or corrosion, okay? So the next part is going to be the extraction of iron, which I will continue in the next video, the last part of topic 4 electrochemistry of this sheet.